Today we're going to have a look at exponential modelling, so just practical situations of exponential functions. We've looked at using exponential graphs to model financial situations, but they're actually also really good for looking at population change over time and bacteria growth, which is, I guess, very appropriate in the current situation. So because we've already covered all the basics of exponential functions, I'll just take you straight through some examples. So our example is when a chef sneezed into a pot of soup, 80 bacteria entered the soup. So that's initially as soon as he sneezed. The number of bacteria increased by 50% every hour. So we need to complete a table of values to show the number of bacteria in the soup over the next 5 hours. So that means we need T or time values from 0 when he initially sneezed all the way up to 5. Okay, so at each hour we're going to look at the number of bacteria because each hour the number of bacteria increases by 50%. So as I mentioned, when T is 0, B, or the number of bacteria, is going to be 80. And then, so when T is 1, the number of bacteria is going to be 80 plus an extra 50% of 80. Now, there's a few different ways we can work that out, but what we're essentially doing is multiplying our value by 1.5 because 150% is the same as 1.5. Then for each of our T values after that, we need to multiply the previous B or bacteria number by 1.5. So at 2 hours, it's going to be 120 multiplied by 1.5, and that gives us 180, and so on and so forth. So we end up with, after 5 hours, there's 608 bacteria in the soup. Now, the next thing we need to do is draw a graph showing the number of bacteria in the soup. So because time is what we call our independent variable, time will move on no matter what. It's on the horizontal axis, it's our x value, and the number of bacteria in the soup is our y value. And so we just plot our values from our table of values in the previous part of the question, and you can see that our graph very quickly takes the shape of the exponential function. Just a note, when graphing, it's a curve, so do not use a ruler to join your plotted points, okay? The whole topic we're doing is on curves, so you need to make sure you draw it with a nice smooth curve. Then we're asked to work out how long it takes for the bacteria to double. So we know the number of bacteria as soon as the sneeze happened was 80. So the number of bacteria we're going to be looking for is 160. And we can just look at that straight off the graph. And because we're looking at it off the graph, it may be a bit of an approximation, but looking at my graph here, I look at the number of when the number of bacteria is 160, my hours is about 1.7. So the number of bacteria has doubled after 1.7 hours. So then the last part of our question asks us asks us to work out the number of bacteria after 12 hours by giving us the equation. So the equation is the number of bacteria is equal to 80 multiplied by 1.5 to the power of T, where T obviously is representing the hours. So it's just a matter of substituting T is equal to 12 into that equation, which is going to give us a number of bacteria of 10,380 to the nearest whole number.